The fourth principle of molecular orbital theory says atomic orbitals will combine to give molecular orbitals only when the atomic orbitals are of similar energy. And this is where we'll start to realize why we can only kind of do diatomics with lower atomic number. Similar energy means better overlap. So what that means is that 1s plus 1s is going to be a good molecular orbital combination because the 1s's are very similar in energy. But 1s and 2s won't give a very good molecular orbital. There's quite a bit of energy difference between them. So 2s plus 2s is good, just like 2p plus 2p would be good, but 2s plus 2p wouldn't be very good. 3s plus 2s wouldn't be very good. As you get to bigger atoms, the higher orbitals begin to mix. So like 3d and 4s are pretty close in energy, actually. They'll start to mix together. And the molecular orbital diagrams get very complicated. Not only do you have more molecular orbitals to deal with, but you start having 3d and 4s mixing with another atom's 3d and 4s orbitals. So it can get pretty crazy. And that's why in this class, we're just going to look at things up to dineon, because up to dineon, 1s only interacts with 1s, and 2s only interacts with 2s, and 2p only interacts with 2p. If you wanted to do, say, chlorine with 3p, well, 3p and 3s mixes a little bit, and 3p and 4s mixes a little bit. The orbital mixing gets a little bit more complicated. So again, this is where the TI 2000 one day will take care of this, but in the meantime, we're stuck with simpler examples. So what combination of atomic orbitals would you expect to create the best molecular orbitals, all right? And again, you want to try and pick the ones which are closest to each other as possible. So 1s and 2p, no, I don't think so. 2p and 3p, probably not. But 3d and 3d, i.e. two that are the same, that's going to be a pretty good combination. Now, it's not that 3d won't mix with 4s or something like that, but the best mixing will be when they're like orbitals, 3d and 3d, just like 1s and 1s, etc. Pretty cool. The last one there, E, 5G. Chemists are close to getting to a 5G atomic orbital. We're right now on the periodic table up to about 118. One day, if we get to 121 protons, that would be an atomic orbital that involves some 5G. So I throw in 5G jokes once in a while, even though we're not really there. Cheesy instructor tricks. So let's build the dilithium molecule. Now, dilithium is kind of special to me because, as I've talked about more than once, I'm afraid, I really like Star Trek. And dilithium was the substance that supposedly allowed the warp drive of Star Trek to work, so they could go different places in no time at all. Dilithium in the real world is a compound that can be made, but so far it has no applications to warp drive theory. Darn it! But anyway, I digress. Dilithium is actually a molecule that can happen. So let's look at this picture here on the left of dilithium itself. The far left is a lithium atom, 1s2, 2s1. The far right is a lithium atom, another 1s2, 2s1. And in the middle right here is the mixing of the molecular orbitals. Now the bottom part is the sigma 1s and sigma star 1s that we saw for hydrogen, no problem. But the top part now is essentially a copycat of that one, where we have a sigma 2s bonding underneath and a sigma star 2s anti-bonding on top. Now, the 1s interactions for dilithium, you have just as many bonding as you have anti-bonding. So the 1s interactions, there's no bonding going along. Those are essentially like lone pairs on the lithium. They're not interacting with the dilithium molecule. But the quote-unquote exciting part happens in the top. You've got two bonding electrons in sigma 1s and no anti-bonding electrons in the sigma star 1s. Notice you've got more bonding than anti-bonding electrons. That means you should have a good molecule. But let's compare it. Let's figure out the bond order. 1/2 parentheses bonding minus anti-bonding. So there's two bonding here, and there's two bonding right there. So that's the 4 bonding electrons. And then right there are the 2 anti-bonding electrons. This one up here is empty. So 1/2 parentheses 4 minus 2, 1 bond order. It's going to be stable. Now, you could have also figured out bond order by just looking at the top orbital interaction. So let's only look at this part right here, and you'd have 1/2 of 2 bonding electrons in the sigma 2s and no anti-bonding in the sigma star 2s. That would also get you to 1. So if you wish to look at bond order only using the top electrons, i.e. the valence electrons in this case, that's totally fine. It's up to you. You can either do the whole molecule or just the top ones. Your call. Lazy chemists a lot of times will look at just the top ones, but honestly, there's nothing wrong looking at the whole molecule. Would you expect diberyllium to exist? Now, beryllium has 1 more electron than lithium. So beryllium would be a 1s2, 2s2. And if you're going to have diberyllium, you'd have 2s2 on the left and 2s2 on the right. And those extra 2 electrons would end up in the sigma star 2s orbital. So diberyllium we would not expect to exist. It would be 1/2 parentheses 4 minus 4 or 1/2 parentheses 2 minus 2, depending on which orbitals you looked at. It's going to have a bond order of 0. If you have just as many bonding as anti-bonding electrons, there's not going to be any stabilization in the molecule, and it shouldn't happen. The next atoms that could make molecular orbitals involve p orbitals. So for example, boron is after beryllium. Boron is 1s2, 2s2, 2p1. And when it comes to the p orbital interaction, it's really cool. So you have 3 2p orbitals from the first atom and 3 2p orbitals from the second atom. You're going to end up with 6 total molecular orbitals, and it's kind of cool. So we're going to see some cool kind of pictures here. The 2p orbitals, first of all, will create 2 sigma molecular orbitals, and the other p orbitals will create pi molecular bonds. So we're going to have sigma bonds and pi bonds when it comes to the 2p interaction. It's kind of cool. And of the 4 pi bonds, 2 of them will be bonding, 2 of them will be anti-bonding. We'll call them pi and pi star. Just like the 2 sigmas, one would be a sigma bonding and one would be an anti-bonding sigma. But there's a little bit of a catch when it comes to the 2 p's. There's 2 different orbital diagrams we're going to be looking at. The first diagram we're going to look at is if you have a boron, carbon, or a nitrogen. And sometimes I think about this as the NBC diagrams. NBC, of course, analogous to the TV network NBC. But anyway, that's just what works for me. If you have a BCN or NBC, notice the picture down here showing the 2p interactions. The 1s's would be down here. They're filled and boring, so not that exciting. And the 2s's, you can see right above it, bonding and anti-bonding are both filled, also not very exciting. The BCN orbitals, the pi's are lowest, followed by the sigma, then the pi star, and then the sigma star. So the pi's get filled in first, and then the sigma, then the pi star, sigma star. I'm going to refer to this sometimes as a 2-1-2-1 diagram because the 2 pi's are filled in first, followed by the 1 sigma, then the 2 pi star, then the 1 sigma star. So for diboron, B2, boron is 1s2, 2s2, 2p1. So that means there would be a single electron on the atomic side for both borons. And when they come together, they both go to the pi 2p shell, so you'd have 1 electron in each side. Bond order, 1/2 parentheses bonding minus anti-bonding. If you look at just the top part, that would be 1/2 parentheses 2 minus 0, because there's only 2 pi electrons. All the other orbitals are filled bond order of 1. So if you have B2, like this one, or N2, or C2, something with B, C, and N in it, then you're going to use this 2-1-2-1 diagram. There's a handout about this and stuff in the companion. You can look it up and stuff and see. However, remember that in the 2p set there on the periodic table, B, C, and N are just the first three. The other three elements are oxygen, fluorine, and neon. So if you have O, F, and Ne, which I will sometimes abbreviate as phone, which is very cheesy, but Phone kind of sounds like phone, and of course we all have phones these days, blah, blah, blah. Anyway, this creates what I'm going to also refer to as the 1-2-2-1 diagram. So if you look at this part here to the left of the line I've drawn, the sigma 2p is now lower than the 2 pi 2p's. In the last picture, the pi's were lower than the sigma, so it was the 2 pi's followed by the 1 sigma, then the 2 pi star and the 1 sigma star. That's why it was the 2-1-2-1. This one is a 1-2-2-1. The sigma is first, the 1 sigma, followed by the 2 pi's, then the 2 pi stars, then the 1 sigma star. So these types of interactions, which are for O2 and F2 and Ne2, which is possible, you want to use the 1-2-2-1 configuration instead of the 2-1-2-1. The bonding orbitals are trading places, but the anti-bonding orbitals stay in the same spots. It's only the bonding ones that kind of make a difference here. This is a picture of dioxygen, O2, and notice how sigma 2p is the first, then pi 2p, then pi star 2p, then sigma star. That's the 1-2-2-1 again for this one. So on this diagram, oxygen is a 2p4. The whole oxygen, remember, was 1s2, 2s2, 2p4. So that means that on each atomic side, you would have 1, 2, 3, and 4. And I'll do it for the other one too. 1, 2, 3, and 4. So you have 8 electrons to put in the middle. The first 2 electrons go to the sigma 2p. The next 2 would go individually to the pi 2p. The next 2 would pair up the pi 2p. And the last 2 electrons, each in their own box, pi star 2p. So bond order here, 1/2 parentheses. And if you're looking at just the 2p, 6 minus 2, that's the bond order of 2. This is going to be a molecule that exists. And since you've been breathing oxygen while you're watching this video, that's probably a good thing. Woohoo! Yeah, go oxygen. Oxygen is absolutely stable, which is cool. Punchline here is that when you get to the boron through neon diatomics, you've got to realize that there's a change that happens between the NBC and the FONEs. And the difference is this is the bonding orbitals, all right? It's a 2-1-2-1 when you get the NBCs, and on these guys, the OFNEs, it's a 1-2-2-1, sigma first, then pi, etc., etc.